Hello everyone, welcome to the Optical Communication lecture series. This is a lecture number 25 and we were discussing about the optical sources. So optical sources we have this chapter we have started into the last lecture. In the last lecture we have studied some points. So we will review some points and we will move on. So what we have studied is we have studied the characteristics of the optical sources. So what are the considerations of optical sources that we have studied? That ability to directly monitor by varying driving current, then fast response time, wideband required for the optical sources, adequate optical power into the fiber. Next is considerations. So what are the considerations that are will require? That stability and efficiency, timing circuit issues, reliability and cost. So these are some considerations we have studied. Then we have seen some PN diodes or how we can configure that PN junction so that the electrons will move on the that higher level to the higher energy level to the lower energy level and that create the photons. So that we have started in the last lecture. Also we have studied some difference between the LED and laser. So these are the some differences that radiatively and non-radiative photons means radiative photons means some energy will be passed through that photons and it will move to the some direction. So that is radiative. And what about the non-radiative? Non-radiative is the different function that will that is not going to not only create a heat, not going to transfer to the one point to the another point. Next is LED versus laser spectral width. So spectral width is very small for the laser, and you can see that for the LED it is very small. LED is having the large spectral width. So that is the difference we were seen in the last lecture. Then light emission. So how that light emission cause? Light emission caused because of the difference between the two energy levels. So that energy level is given by the HV. That is H is the Planck's constant and V is the velocity. That we have studied that how the HV is created. So you can see that HV created you because of the different two energy levels. So two energy levels is E electric field and magnetic field. So by that way it will create the energy levels, energy bands. So you can see here there is a two different energy levels are available here, 2 kT and 2 kT here. That having that, if suppose there is from the same holes and electrons are there in upper and lower band, then it will be a create that difference will be equal. Next we have studied that n type of material. So n type of a material having the donor quality means there will be having the extra electrons as compared to the holes. So there is a extra electrons available above that higher level than as compared to the lower level. So you can see here that the figure in this figure B, we can see that higher level if electrons having the higher electron concentration distribution, and for the below it is hole concentration distribution. Next is P type of material. P type material having the conduction band with a less number of electrons and a high number of holes, so that it is called as an acceptor. So acceptor, that is level, that is called as EA. So group 3 is having the acceptor part. Next we have started with a light emitting diode. So light emitting diode, how it works. So response time and high quantum efficiency is the characteristics of the LEDs. Double or single heterojunction devices, surface emitting diffuse radiation versus edge emitting more directional LEDs are there. So this is the LEDs. Now heterojunction means what? There is a uh, one or two or more n-type material and p-type material is available. So I have shown you one figure. In that we will see. So the p-n junction of the basic gallium arsenide LED laser described before, it is called as a homojunction because only one type of a semiconductor material is used in the junction and different dopants to produce the junction itself. The index of refraction of the material depends upon the impurity used and the doping level. So heterojunction we have studied. So this is, I have shown you the diagram that heterojunction. So heterojunction having uh, so heterojunction is having this type of structure. This type of a structure, in that two n type material is there and two p type material is there, and there is a middle section is available, that is n recombination process where occur. Next we have studied. Now we are going to the next point, that is today we are going to start with this lecture, that operating wavelengths. So which are the operating wavelengths are there? Already we have studied that our different operating wavelengths. So you might be have heard many times from me that 850 nanometer is there, then 1300 nanometer is there, 1550 nanometer is there. Also I have shown you the graph where different wavelengths are there, different wavelengths were available, and from that different wavelengths we were discussing, we were using one particular wavelength, that is 1550 nanometer. Why? Because we have seen that with there is in the 1550 nanometer wavelength there is a very less amount of loss is there, that almost 0.2 dB per kilometer. So that is nanometer wavelength is having that much less loss is available, but as compared to that 850 nanometer and 1300 nanometer having the higher losses. Semiconductor sources are designed to operate at a wavelength that minimize optical fiber absorption and maximum system bandwidth. So that semiconductor devices will work on this wavelength of minimize optical absorption. So optical fiber absorption should be minimized and the maximum system bandwidth. So LED wavelength is given by lambda micrometer, that is 1.2399, that is divided by E, that also we have studied. Lambda is equal to wavelength in microns, which is the Planck's constant. C is the speed of the light, E is the photon energy, that is in the electron volt. So these are the different band gap energies. You can see the possible wavelength ranges in the various materials. So there are the different band gap energies for the indium phosphide, then indium arsenide, gallium phosphide, gallium arsenide, then aluminum arsenide, then gallium indium phosphide, aluminum gallium arsenide, indium gallium arsenide, and indium gallium arsenide phosphide. So these are some materials. So these are material you will require when you will give the answers for the reality, that suppose they will ask the question on the uh, semiconductor material used for the optical source. That time you have to give these alloys and you have to tell, you have to write like how the alloys can be work and how the alloys will work as a heterojunction material, so that the heterojunction material will be work for the systems. Semiconductor light emitting diodes. Semiconductor LEDs emit incoherent light. Spontaneous emission of light in a semiconductor LED produces a light wave that lack of fixed phase relationship. Light wave that lack a fixed phase relationship are preferred as a incoherent light. So these are the some characteristics of the LEDs. The use of the LEDs in a single mode system is severely limited because they emit unfocused incoherent light. So these are the some, if they are characteristics, they have some drawbacks. That is the drawbacks of the incoherent means it will coherent means it will go in a straight line or it will go in a particular direction. But LED we can't use in a single mode fiber, because you have seen that in a single mode fiber the only light will go into the straight line. It will not hit to the boundaries of the core or cladding. It will go into the straight line, like it will suppose I will draw here a figure. So suppose there will be, this is optical fiber. In that optical fiber, so the light will go like a straight line. So it will not hit this core. It will not move like that. It will go to the straight line. So this is coherency, and this will not useful in a single mode fiber. In the single mode fiber, as I shown this arrow, this is the only direction that waves will be travel. So that's why for a longer distance we are using a single mode fiber as compared to the multi-mode fiber. Multi-mode fiber having the more losses compared to the single mode fiber. So that's why we are not using LEDs into the single mode fiber. Even LEDs developed for a single mode system are unable to launch sufficient optical power into single mode fibers for many applications. So that is again a drawback of the single mode fiber. LEDs are preferred to optical sources for multi-mode system because they can launch sufficient power at a lower cost than the semiconductor LEDs, laser diodes. Next is semiconductor laser diodes. Semiconductor laser diodes emits coherent light. What is meant by coherent light? That as it should be a directional, in the particular direction it will be going to the straight line. So LD produces light waves with a fixed phase relationship, both spatial and the temporal, between the points on the electromagnetic waves. So suppose there will be electromagnetic waves and both have waves or two waves are there, then it will be a relationship between spatial and temporal, means in the space and the time domain, space domain and time domain, there should be a synchronous, they both should be a synchronous. At time these semiconductor LEDs will support that coherency, so that it is useful for the coherent technology or transmission of the light. Light waves having the fixed phase relationship are referred to as a coherent light. So coherency is fulfilled by these semiconductor LEDs. Next is semiconductor LEDs emit more focused light than the LEDs. They are able to launch optical power into the both single mode fiber and multi-mode fiber. So that we can see now it is preferably you are using in the single mode fiber, but in the multi-mode fiber also, if it is coherent and it is spatial and temporal domains are synchronous, then we can use it into the multi-mode fibers also. So that is the good point about the LEDs or laser diodes. So laser diodes are usually used only in a single mode fibers system because they require more complex driver circuitry and cost more than the LEDs. So laser having that drawback, that having the heavy cost, because laser is having the highly qualified and highly quality structure, and it will be laser will give the waves which is in the straight line, or it will be having the less loss with a coherent direction. Then we have to pay some more cost as compared to the LEDs. So laser having the highly cost, and because of that it should be in coherent, it should require a high coherency for the system. Produced optical power. So we have to compare that optical power for the both LED and lasers. So optical power produced by the optical sources can range from the microwatts for the LEDs to tens of milliwatts for semiconductor LEDs. However, it is not possible to effectively couple all the available optical power into the optical fiber for transmission. So it is 100% efficiency is not possible for any system, that if you are giving the suppose 100 watt power if you are giving, then it will be utilized 100 watts will be utilized, it is not possible. So something will be lost, will occur inside the optical fiber. So because of that, it is not possible for both for LEDs or the lasers to convert that power into the 100% power. So it is not possible. Dependence of coupled up power. The amount of optical power coupled into the fiber is the relevant optical power. It depends on the following factors: the angle over which the light is emitted. So we have seen that acceptance angle, critical angle. If the optical power is coincide with the critical angle, then it is most of the power, as I said, we can't say 100%, but most of the power we can capture inside the optical fiber. The size of the source of light emitting area relative to the fiber core size. The alignment of the source and fiber, the coupling characteristics of the fiber such as the numerical aperture and refractive index of the profile. So these are some definitions of the optical power required. Typically, semiconductor lasers emits light spread out over the angle of 10 to 15 degrees. So 10 to 15 degree angle should be there. Means what? There should be angle like uh, suppose there will be an angle, that angle should be 10 degree or 15 degree. 15 degree. So like that the angle should be there. Semiconductor LEDs emit the light spread out at even larger angle. So semiconductor LEDs having the larger capacity, coupling loss of the several decibels can easily occur when the coupling light from the optical sources to a fiber is, especially with the LEDs. Source to fiber coupling efficiency is a measure of the relevant optical power. So source to the fiber coupling efficiency is a measure of relevant optical power. The coupling efficiency depends on the type of a fiber that is attached to the optical sources. So coupling efficiency is more required or more used. Coupling efficiency also depends on the coupling techniques. So which are the coupling techniques that we will study? Current flowing through the semiconductor optical sources causes it produce a light. So that is the conversion of electric energy into the light energy. LED generally produce the light through a spontaneous emission when the current is passed through them. So what is spontaneous emission? So that we will study. Spontaneous emission is the random generation of photons within the active layer of a LED. So how the spontaneous emission, that we will study in detail in the next lecture, but in this lecture we will study that how in the LED light will generated. The emitted photons move to the random direction. Only a certain percentage of the photons exists in the semiconductor and coupled into the fiber. Many of the photons are absorbed by the LED's material and the energy dissipated as a heat. So that is called as a spontaneous emission. Means spontaneous emission means the light will be generated in anywhere and it will convert that will be converted into the photon energy. So that we will study how to convert that into the photon energy, that light. So that's it for today. We will study in brief for the LED into the next lecture. We will move on to the different sources into these lectures. In few lectures we will cover this third chapter. It will it will require 3 or 4 lectures for to complete this third chapter. So we will meet into the next lecture. Till then, thank you.